Good everyone. We are back again on our recording session 5, titled The Diagonalizations of the Symmetric Matrix. Diagonalizations of the symmetric matrix. We can still recall from our previous knowledge of the symmetric matrix. The symmetric matrix is when you have a matrix A, and when you find the transpose of that matrix A is equal to that matrix A. That is to say that particular matrix is symmetric. So we are still continuing in that knowledge. So you recall the symmetric matrix A, which is equals to A transpose. Then we have orthogonal matrix. An orthogonal matrix A means that the inverse of matrix A is equivalent to the transpose of A. If you can find a matrix of such, we say that particular matrix is orthogonal matrix. Then 3. Orthogonalities of matrix implies symmetric. Orthogonality of a matrix implies symmetric. That is, if a matrix is symmetric, that is, the orthogonalities of the matrix, it means that that matrix is symmetric. But in the other way around, symmetric matrix may not necessarily imply orthogonality. Then we look at a diagonal form of a real symmetric matrix. A diagonal form of real symmetric matrix. Let D of lambda 1, lambda 2 up to lambda n, that is, the diagonals of that matrix is given as this. Be a diagonal matrix with diagonal elements, that is, the element of that matrix. The diagonal elements are lambda 1, lambda 2 up to lambda n. The matrix D, that is the diagonal matrix, is called the diagonal form of A. When you have D of lambda 1, lambda 2 up to lambda n, is called the diagonal form of the matrix A. And the equation x2 is equal to the diagonal of lambda 1, lambda 2 up to lambda n of x1. That is how you find your constant, your lambda. You can still recall from the eigenvalue. So we are still saying the same thing here. We should represent the corresponding operator in the diagonal form. So let's look at the theorem to prove that existence theorem. If A is a real symmetric and lambda 1, lambda 2 to lambda n are its characteristic roots, then there exists an orthogonal matrix U such that U transpose multiplied by AU is equal to the diagonal matrix. Is equal to the diagonal matrix. That is equal to the diagonal of that matrix, which is given as the D of lambda 1 to lambda n. A square matrix is called a diagonalizable. A square matrix is called diagonalizable if there is an invertible matrix P such that the inverse of P multiplied by AP is equal to B. That is, you can say a square matrix A is diagonalizable if there exists a matrix P with an inverse. So when you multiply that matrix P with your A, so you will have, that is the identity the inverse of that matrix existed. So P inverse multiplied by AP is equals to B, where your B is a diagonal matrix. The matrix P is said to be a diagonalized A. You should note that definition. That is, a square matrix is called diagonalizable. For a square matrix to be diagonalizable, there must exist an invertible matrix P such that the inverse of P multiplied by AP is equal to B, whereby your B is the diagonal matrix. The matrix P is said to diagonalize A. And this definition is what we are going to make use in finding the matrix that diagonalize another particular matrix. If A is an n by n matrix, then the following are equivalent. If A is n by n matrix, that is the square matrix, so the following are equivalent. 1. A is diagonalizable. That is, if you have a square matrix, it will be diagonalizable. 2. A has linearly independent eigenvector. A has linearly independent eigenvector. Think you can still recall from the knowledge of finding your eigenvalues and eigenvectors. So let's prove that. Suppose that A is equivalent to, suppose 1 is equivalent to 2. That is, suppose we have a matrix A which is diagonalizable and is also A is linearly independent eigenvectors. We want to establish that. Since A is assumed to be diagonalizable, then there exists a many invertible matrix P, and the P is given as the matrix you have as a P11, P12 to P1n, that is n by n matrix, such that the inverse of P multiplied by AP is equal to the diagonal, where the diagonal is given as lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, and so on. So you have a diagonal matrix which is equivalent to AP equals to PD. That is a diagonal matrix. So the next one is to see that our AP is when you multiply your A multiplied by the diagonal. So you have the matrix, the product. Let P1, P2 up to Pn denote the column vectors of P. Then, from the result above, the successive columns of AP are lambda 1 P1, lambda 2 P2, up to lambda NPN. However, the successive columns of AP are AP1, AP2, up to APN. Thus, we must have AP1 to be equal to lambda 1 P1. Then AP2 to be equal to lambda 2 P2, and so on. P is invertible. It implies that its column vectors are not zero. And from the multiplications you have there, you will have your lambda 1, lambda 2, that is, find the values of your lambda up to lambda n are eigenvalues of A. And the corresponding eigenvectors, which is P1, P2, up to Pn. These eigenvectors, which is your P, are linearly independent since P is invertible. Since you can find the inverse of P, so that your P are linearly independent. Thus, A has and linearly independent eigenvectors. On the other hand, suppose that 2 is equal to 1. Suppose 2 is equal to 1. That is, suppose A has linearly independent eigenvectors. Suppose A has linearly independent eigenvector is equal to a diagonal matrix. Is equal to a diagonal matrix. So we want to prove that. Assume that A has linearly independent eigenvector P1, P2 up to Pn with corresponding eigenvalue lambda 1, lambda 2. Let P be this. Be the matrix whose column vectors of the products AP are AP1, AP2 up to APn. But AP1 equals to AP1 lambda 1 P1, AP2 equals to lambda 1 P1, and so on. So we are trying to establish that the orthogonality of the matrix implies the symmetry of that particular matrix. So we can see from the problem that your AP is equivalent to your BD, where D is the diagonal matrix, having the eigenvalues lambda 1 up to lambda n on the main diagonal. But the column vectors of P are linearly independent. This means that P is invertible. Thus, the inverse of P multiplied by matrix A and P is equivalent to the diagonal. Therefore, A is diagonalizable. So we want to optimize the steps for diagonalizing a matrix. Step 1. The first thing is to find the n linear independent vectors of A. That is, your P1, P2 up to Pn, depending on the number, depending on the matrix, whether it's n by n matrix. So the second step, you form matrix P, having your P1, P2 up to your Pn as its column vectors. Then the third one, the matrix P, that is, the P inverse multiplied by AP will then be the diagonal matrix D, with P1, P2 up to Pn as its successful diagonal entries, where lambda is the eigenvalue corresponding to P. So P, you take values perhaps P1, P2, depending on the dimensions of the matrix. So let's look at example now to further explain what we are talking about. Determine the matrix which diagonalizes the following matrices. Determine the matrix which diagonalizes the following matrices. You have your matrix A, you have your matrix B. So we'll look at the first one, while the second, the B part, will be given to you as an assignment. Solution. The characteristic equations of that matrix A, now you have given the matrix A, which is 0, 0, minus 2, 1, 2, 1, then 1, 0, 3. That is your matrix A. So you find the characteristic equations of that matrix, which is the determinant of A minus lambda I know your A, which is the matrix given to you. You know your lambda, which is the characteristic polynomial. Then your I is the identity matrix. So in this regard, you know what your I will be. It's going to be a 3 by 3 identity matrix. You find the determinant, which is equal to 0, for us to be able to determine the lambda. So you have it as 0, 0 minus 1, 1, 2, 1, 1, 0, 3 minus the identity matrix. So here I've multiplied the lambda by the identity. So I have it as 0. I have it as lambda 0, 0, 0 lambda 0, 0, 0 lambda, which is equals to 0. So when you perform the arithmetic operation here, you subtract this one from this. So you have the next value, which is the determinant of minus lambda 0 minus 2, then 1, 2 minus lambda 1, 1, 0, 3 minus lambda, which is equal to 0. So you know the idea of finding the determinant of the matrix. You pick the first column, you cancel the first row and the first column, you multiply the remaining one. So when you apply that technique, you will have your equation. You have your polynomial equations as 5 lambda, which is equal to lambda raised to power 3 minus 5 lambda square plus 8 lambda minus 4 equals to 0. This is a characteristic equation. So you solve this polynomial equation now. You know the polynomial equations of degree 3. That means you are going to have 3 roots. So you have 3 values for your lambda. So the first thing to do is to find the roots of that equation. You look for a number that you can substitute that will give you 0. So when you get that number, here the number is 2. So that means 2 is one of the roots. So when you put 2, you use your long division method to break down the polynomial. So you reduce it to a square to a quadratic equation. So you will have it as lambda minus 2, then lambda square minus 3 lambda plus 2. So from there, the first one you have lambda equals to 2. Then you solve the other equations, which is quadratic equations. So we have it as 1 and 2. That means the hidden values of A is now given as 1 and 2 twice. So you have 2 and 1. So the hidden value now is 1, 2, and 2. So you will go back to your characteristic equations. So when your lambda is 2, you go and substitute the values of lambda into that equation. Then you solve for your x1, x2, and x3. So you continue like that. When your lambda is 1, you substitute the value there, you get your x1, x2, and x3, which is your corresponding eigenvector for lambda equals 2. So for lambda equals to 1, you also get your corresponding eigenvector, your x1, x2, and x3, which are given here. So this will now form the diagonal, the diagonalizable matrix that we are looking for. So we have your P1, P2, P3. You can still recall from the proving, you will get your eigenvalue. Having gotten your eigenvalue, then you get your eigenvector, and that eigenvector is the one that will form the diagonalizable matrix that we are desiring for, which is your P1, P2, P3 up to your Pn, depending on the dimensions of the matrix given to you. So we have here as a P1, P2, and P3, which is equivalent to 3 by 3 matrix, minus 1, 0, minus 2, 0, 1, 1, then 1, 0, 2. So we have it as our P in matrix is diagonalizable and P is equal to that. So you verify now. You want to verify whether the inverse of P multiplied by AP is diagonal. So you check that by finding the inverse of your P. Now to find the inverse of the matrix, find it, then use it to multiply your AP. You will discover that you will have a diagonal matrix, which is given as 2 0 0 0 2 0 0 0 1, which is given as our D. So the B aspect of it left as an exercise for you to be submitted. You upload it on your LMS. That is matrix B. Remark, there is no preferred order for the column of P, since the height diagonal entries of P inverse AP is an hidden value for the IT column vectors of P. Changing the orders of the vectors of P just changes the orders of the hidden values of the diagonals of P inverse AP. The orthogonal diagonalization. We want to define the meaning of orthogonal diagonalization. If given a matrix A of order n, and if there exists an orthogonal matrix P such that the inverse of AP, the inverse of P multiplied by AP is equal to the transpose of P multiplied by AP, and they are both equal to the diagonal matrix, which is labeled as your equation A. And where your D is the diagonal matrix, then the matrix A is set to be orthogonally diagonalizable. So for a matrix to be orthogonally diagonalizable, the inverse of P multiplied by AP must be equal to the transpose of P multiplied by AP, and both must equal to the diagonal matrix. That is the definition. Where your P is the orthogonally diagonalized A. For a matrix, say A, to be orthogonally diagonalizable, the matrix must be symmetric. It must be symmetric. That is, that matrix, the transpose of that matrix and the array matrix must be equal. That means that the transpose of A must equal to A. This can be shown that A transpose is equal to A, implies that the transpose of P multiplied by AP is a diagonal matrix. P is orthogonal. Then D is the diagonal. Implies that the transpose of P multiplied by P is equal to P multiplied by the transpose of P, which is equivalent to the identity matrix. Therefore, A is equal to PAD transpose D. A is equal to PD P transpose, where your D is the diagonal. That is, the diagonals of the transpose of the diagonal is also equal to the diagonal. Therefore, the transpose of A is equal to P D multiplied by P transpose, or you take the transpose of the whole matrix is also equal to the P multiplied by the diagonal multiplied by the P transpose, which is equivalent to your A. Therefore, your A transpose is equal to A. Implies that A is a symmetric matrix. Should be able to establish all these facts. Diagonalizing a symmetric matrix. How to diagonalize a symmetric matrix? Theorem. If A is a symmetric matrix, then 1. The eigenvalues of matrix A are all real matrices. The eigenvalues of the matrix A are all real matrices. That is the value you get, your lambda. They are all real matrices. Then 2. The eigenvector from different eigenspace are orthogonal. From the above theorem, a symmetric matrix A can be diagonalized as follows. 1. You find the basis for each eigenspace of A. Apply the Gram-Smith process to establish this base to obtain an orthogonal basis for each eigenspace. Form the matrix P whose columns are the basis vectors constructed into the matrix then orthogonally diagonalize A. Orthogonal diagonalization is given a matrix A of order n, and if there exists an orthogonal matrix P such that the inverse of P multiplied by AP is equal to P transpose multiplied by AP equals to the diagonal, where your D is the diagonal matrix, then the matrix A is said to be orthogonally diagonalizable, and P is said to be orthogonally diagonalized A.